So good afternoon everyone. I am Palak. I am a PhD student in soft condensed matter group and I am working under the guidance of Professor Anjani Bandyopadhyay. So the title of my talk is Control of Interfacial Instabilities using, okay, I can remove my mask maybe. Yeah. So the control of interfacial instabilities using a non-Newtonian fluid. So as the title suggests, it's like interfacial instability. So today I'll be talking about the interface between the two fluids, and one of the fluid is non-Newtonian fluid. And so what is all about, like interfacial instabilities? So you have two fluids, and when your less viscous fluid displaces the more viscous one, so then it gives rise to the formation of intricate patterns. And this is always the case when more viscous is displaced by the less viscous one. Now what we want to see, like what will happen if you take one fluid to be complex enough, like the non-Newtonian one, and how will it affect these patterns, like how will it affect the morphologies of these patterns. And so these kind of patterns you see everywhere. So before proceeding to that, I just want to mention, like, this work is done in collaboration with Weber, who is sitting over there, and my senior Debashish Shah, who is in right now in University of Düsseldorf doing his postdoc there. So yeah, so as I was talking about the patterns, like the nature is full of these patterns. You see a lot of these patterns around you. For example, in the tree branches, mud cracks, in the river network formations, and even in human lungs also. So in this case over here, like the tree branches, so have you ever wondered why the tree branches grows in this way? I'll tell you. So these tree branches grows in this way to get an optimized light exposure for its leaves and oxygen exposure for the tree. So this whole process of like this branching and all has a motive of like getting an optimized function to grow. And even like this one fascinates me a lot, this example. So the human lungs, you see these morphologies in the like the vertebrate airways. So imagine if human lungs don't have this branch network. And imagine a simple shape, say like a sheet. So now this has some area, right? So imagine if it would have that sheet shape. So the equivalent area required to do their function, the same efficiency as they are doing right now, well fitted in our body, will be equivalent to 2 tennis courts. Imagine that. So that's the importance of these branch networks, like this is important. But let me tell you, this is not always like, okay, we want the intricate patterns, these are so fascinating. There are certain fields where you don't want these instabilities to occur. You don't want these interface instabilities to occur, those patterns. You want a stable, beautiful interface between these. So the area is like, basically the one where from this whole problem is originated is the petroleum industry. So during the extraction of crude oil from underneath, so water is pumped with high pressure to extract the oil from the porous band, and there these tons of water were absorbed while like during the recovery. So that affects the efficiency, right? Like the extraction of the oil. So there you don't want this instability. So our motive is like, okay, we need a control, we need an active control of these instabilities, okay, whether it's enhancement of these instabilities or their suppression. So we should be able to control this. Depending on our requirement, we can do it. Now all these things are like very large scale process, right? So how to do it in our lab? How to do it in lab? So that's what we are doing in our lab, like we are controlling these instabilities by using non-Newtonian fluids. Okay, so the system, as I said, like one of the fluid we are using is a non-Newtonian fluid, which doesn't follow the Newton's laws of viscosity. It shows the complex flow behavior. So the one which we use is the laponite, which is a synthetic clay. So unlike the natural clays like bentonites and all, it has like a lot of polydispersity there. This is a synthetic clay which has like this monodispersed dish-shaped particles. So having diameter 25 nanometer and about a nanometer thickness. So on the top left side, what you are seeing is a schematic like showing the laponite structure. So it's an inorganic molecule having octahedral sheets sandwiched between 2 tetrahedral sheets containing these elements over here. Okay, so as I was telling, so this laponite comes in the powder form. It's a white powder, and which by the way is very hygroscopic. Basically it absorbs moisture quite fast. So before any kind of use, you need to bake it in oven to remove all the moisture. So as I said, like these are dish-shaped particles. So in its original form, it forms like these tectoids, the stacks of these dish-shaped particles. Now, what will happen when you dispose this powder in water? So these blue things are like the laponite disk, having sodium ions in the intergallery space. So when you dispose these laponite particles in water, so the sodium ions start coming out in the bulk due to the osmotic pressure gradient. And as a result of this, the sodium ions is Na positive, right? It comes out, so it gives a negative charge on the face of this particle. Now these two disks have like the negative charges on their faces. They start feeling the repulsion force. And as a result of which they like fall apart, like it exfoliates, and you have these separate laponite particles. So, the charge on the rim is pH dependent, like in which medium you are suspending these particles. So for example, in water, so deprotonation at the rim of these laponite particles give rise to a slightly positive charge on the rim. So this whole process like happens over time when you dispose it and the sodium ions are coming out and all. So the time-dependent electrostatic interactions between these heterogeneous charged particles give rise to the formation of this kind of microstructures. So this is a schematic of like commonly used house of cards structures, basically this arrangement you are seeing over here. So this positive on the rim and the negative phase charge, these laponite particles are forming this kind of structure. So just by merely like this system is like evolving with time. So you just keep the system for time and then it transforms itself. So it ages, that's how, like this whole process is happening with time. That's why people call it as an aging material also. So we just add the powder in water, stir it for enough time and then filter it to use for the experiments. Okay, so I'll just show you one layer this thing. So this is a photograph taken like just after the sample preparation. So this is a glass vial, and by this you can see it's a liquid-like, right? When we tilted it. So what we have done is like we kept it for a day, 24 hours, keeping it undisturbed and taking care of the evaporation. There shouldn't be any evaporation. I'll show you. After 24 hours, it transforms into a soft solid. So when you tilt the bottle, it's sustaining its own weight. So this is a very beautiful system, nothing to do with it. Let's just give it its time and it transforms itself. So now we are talking about this viscoelastic material, this non-Newtonian fluid, which has the both viscous and the elastic property because it's getting solid, right, with the time. So it has this both viscous-like properties also and the elastic properties also. So we have done some rheology, which is the study of the flow and deformation. So you apply some, you see like how the flow will be when you apply some deformation to the material. So I will not go into the very much detail. So just think like, okay, on the left-hand side you have one plot where on the y-axis you have these two symbols, G prime and G double prime. So this G prime is basically the storage modulus, which tells you about the viscoelastic solid-like behavior of your material. And G double prime tells you about its viscoelastic liquid-like behavior. So these two parameters tells you about both the viscous and the elastic behavior of the system. And on the x-axis, you have the waiting time. So waiting time or aging time, I'll use it interchangeably. So this is the time for which you are keeping your sample. So if you see over here, these solid symbols are basically your G prime, and the hollow symbols are your G double prime. So at initial times, you see like the G double prime is dominating over G prime. That means in this time regime, it's behaving like a viscoelastic liquid, as you can see from here also, like it's a liquid-like. But you wait for enough time, and like with time, so G prime starts dominating over G double prime. That means the system is becoming like solid-like, and its elasticity is increasing because G prime is increasing and it's more than G double prime. So this is the time regime where you have this like the formation of these structures which give rise to this rigidity to the sample, and that's how it's becoming elastic with waiting time. And on these two plots here is the flow curves, which basically just tells you about this viscosity versus shear rate variation. So as I said, these are non-Newtonian fluids. So this one is for laponite suspension. So it doesn't follow the Newton laws of viscosity. That's why here you are seeing like its viscosity is changing with the applied shear, like the applied deformation. So these different colors over here are the different times, waiting times. You can see that this is on the log scale. So you can see like there's a change in the viscosity, but our main concern is about the elastic property of this material. And the bottom is the other two fluids. As I said, interface instability is about the two fluids, right? So the one fluid is the laponite suspension, and the other two fluids, like the different fluids, is the water and mineral oil. Both are Newtonian fluids. That's why their viscosity is independent of the applied shear rate. I'll tell you like what's the reason behind using these two different fluids like water and mineral oil. But in one set of experiments, it's like a displacement of laponite suspension with water. In the other set of experiments, it's the displacement of laponite with mineral oil. So with water is something like you have laponite in water, so the water mixes well with laponite, right? In the second case, mineral oil doesn't mix with water, right? So it has this interfacial tension, the surface tension between two fluids. Okay, so as I said, like to study these instabilities on the laboratory scale, people do often use radial Helical cell, which is just like, it comprises only 2 circular glass plates. The main condition is like you should have the confinement very less. So here is like 170 micron gap between these 2 plates. And the top plate has this central hole. So with the help of this hole, we fill first the aqueous laponite suspension in the cell, and then the second fluid, either water or mineral oil, is injected in the same cell. And we look at the profile between these 2 fluids, like how the interface will grow in the different scenarios. And yeah, so we inject the fluids with the help of a syringe pump, which decides like what should be the pressure like to fill the fluids, like to displace the fluids. Okay, so as I told you about this waiting time, right? It ages with time, it transforms with time. So let's see, so what we have done is like you prepare the laponite suspension, we filled it in the Helical cell, and then waited for this time, this predetermined aging time. Then we have injected the second fluid, like see how it reacts to the, like the inner fluid which is displacing it. Can you see at low ages when it was like liquid-like sample? So this dyed thing is the dyed water over here, and the gray background is basically laponite because it's transparent, so it's the sheet color which you are seeing from the top. So as you see, like at low ages, it's like a dense viscous patterns, like you have these fingers and they are constantly merging. Now let me show you what will happen if you increase the waiting time. Okay, so now you have the well-defined boundaries and you eventually got this dendritic profile of the interface, dendritic patterns having these side branches. As I told you, like with the time, so its elasticity is increasing, it's becoming like solid-like. Till now, it's like the displacement, right? It's displacing. Now let me show you, if you waited enough for a day, okay, it actually fractures the outer media. It actually fractures the laponite suspension. So just by like a single concentration, a fixed concentration, fixed displacing rate, we have observed a wide range of interfacial patterns with the system. And if I, okay, yeah. So these are the different patterns you see on the screen as the different waiting times, this TW. So we have observed the transition from dense viscous pattern to the viscoelastic fractures with the dendritic patterns at the intermediate waiting time. Now, as I told you, this was about like the displacement with water. So now what will happen if you incorporate interfacial tension also? So everything will be same, these waiting times, the displacing rate, the flow rate will be same. It's just the inner fluid, basically the fluid which is displacing laponite is replaced with mineral oil. Okay, so now you no longer have those fractures. Though the elasticity and everything is the same, outer media is same, everything condition is same, you have this additional interfacial tension between the 2 fluids, and we eventually see the flow stabilization effects of this interfacial tension. So we observe this flower pattern at the low ages of laponite suspension, like you see this like the flower petals, the thick protrusions, and at high ages, we saw this like the jagged pattern. So jagged, basically you can see like this, the curvature, the jaggedness at the interface. So again, just the simple single fluid pair, we have observed a wide range of interfacial patterns. But that's not just the end of the story. So what will happen, as I was telling you, like the displacing rate is same and everything. So what will happen, okay, we know like something is definitely happening at the high ages where the suspension is in the elastic state, it's becoming solid. So what we have done, like, okay, we fill the laponite, wait for 24 hours. Now what we have changed is like the displacing rate, with the pressure with which you are displacing it. So we have got the same sequence, we have restored the same sequence of interfacial patterns just by changing the flow rate, like the displacing rate. So we have seen like the viscoelastic fractures at low injection rate, and at high injection rates, we have observed this dendritic pattern. So basically, what is happening over here? So you have this formation of structures, right? So by increasing flow rate, what you are doing, you are disrupting those structures formed in your suspension. So at low flow rates, your elasticity is sustaining those applied pressure. That's why you have this viscoelastic fractures. And at high flow rates, you have this dendritic pattern. Similarly, over here, we have observed the same transition from jagged pattern to the flower pattern with increasing flow rate. So just by like using a single fluid pair and using its aging property, we have observed this wide range of interfacial patterns. Now, we have seen these features, right? Now we need to quantify them, like how we can quantify, how we can know like what are these patterns, what will be the pattern, what will be its quantity, who can tell us like which kind of pattern it is. So we have calculated a ratio, which is the ratio of two areas, AP by A. So AP is the pattern area. So here the gray background is your laponite and the black again is your inner fluid. So this black portion area, the area of this pattern is AP. And the pi r square is the area of the circle which comprises this whole pattern. So it's a fully developed pattern. It's at the later stage. So it's not at the onset. It's a fully developed pattern. So by just using the areal ratio, we are like quantifying these patterns. Okay, so here is this ratio versus the waiting time. The first parameter which we saw is the aging time, right? So here you can see like from just by looking at the patterns, you will see, okay, yeah, this should have the more ratio, like more area, and compared to this one, this is what is reflecting over here. So the black squares you are seeing is for the miscible case, like for the water case, the black patterns, and the red ones are for the mineral oil case. So as from the patterns, you can yourself like see, like, okay, so this in this direction for the miscible case, the areal ratio is decreasing, and for flower pattern to jag pattern also is decreasing. And since this immiscible case is like where the interfacial tension is there, so it's more thicker protrusions and all. So for all the sets of experiments, the areal ratio for immiscible displacements, like immiscible patterns, are always greater than their miscible counterparts. Similarly, for the case when we plotted this versus Q, which we have changed in the second set of experiments. So there also we have seen like there is a change in the areal ratio, the similar changes in the areal ratio with the increasing flow rate also. Now, what we want to see, like, okay, so we have seen these morphologies, the areal ratio we have seen. Now I want to tell you, like, this just by the areal ratio, we have segregated all the observed morphology in a single phase diagram, spanned over the waiting time, your flow rate, and of course the interfacial tension between the two fluids. So these are the different morphologies which we have segregated on this phase diagram. And the colors over here shows the different morphologies. And these are the values, like the colors are corresponding to the logarithm, natural logarithm of this areal ratio. I want to tell you, like, as I said, it's about the control of instabilities, right? So we do have observed this stable interface also with the same system. If you displace a low-aged laponate suspension with a high flow rate, like mineral oil, you can eventually suppress the whole instability and like end up having these stable interfaces. So that's the moral of the story. So by just using this clay suspension, one can control the instabilities and these shear and the time dependent, like the time dependent, basically the aging time, and this shear dependent rheology, depending on the flow rate, can actually go on to the pattern morphology. And this is the first time when the aging time of this clay suspensions has been used to control these instabilities. So this, we propose that like this can be a reliable control parameter in future to control these instabilities. And of course the pattern areal ratio, just the ratio of the areas of the, like the pattern with the area comprising it, can actually segregate the whole wide range of morphologies. And plus this study can help in like predicting the interfaces in the case of like the mud and slurry displacements. So I would like to thank Professor Anjani for the good and engaging scientific discussions and like to come up with this and her guidance in the work. Of course, my lab mates and the workshop people for their help with the experimental setup. Is Vaibhav and is Debashish. Thank you guys for your attention.